differential and integral equation, especially integral equation, because we said whenever we have a differential equation, first we convert into some integral equation, and once we have an integral operator, then we can state its property and we can apply the some suitable formula for that operator. So I welcome sir again, and I request sir, so please.
Thank you.
Thank you.
Okay, so as you have seen in the last lecture, I had discussed the basic contraction principle and its extensions. So now, as promised, I am going to discuss its applications to differential equation. So in differential equation, we have two types of problems: initial value problems and boundary value problems. Okay. So let's start with an initial value problem. So usually all practical problems are of even orders. Of course, for completeness sake, we get odd order differential equation, and in certain problems you may encounter those odd order problems, but in most of the applications you have second order problems or even order problems. So let's take a very simple case like this. Sorry, y prime. I will not consider that y prime term, but you can in general include that also. So because we are talking about very simple examples here, and so here x is greater than 0 or x can be greater than some point x naught, but for simplicity we will take the starting point as 0. Okay. And then you have two initial, because it is a second order, so you have two initial conditions, that y 0 equal to a and then y prime 0 equal to b. Okay. So as you know, we are going to consider the applications of this fixed point theory. So we will convert it to an integral equation, and here, so what do we simply integrate those derivatives. So first integration will lead to this y prime x equal to y at 0 is a, and then you have plus integral this 0 to x f t dt, and then you have minus lambda 0 to x y t dt. Okay. Sorry, this should be b, y prime at 0 is b, and then second integration will give us y x equal to a plus b x plus, you have now double integral 0 to x and then 0 to t, and then f s ds and then dt, like that. You dummy variables keep changing. So 0 to x again, and then 0 to t y s ds and then dt. Okay. Now to get rid of these double integrals, we use the theorem. In general, what we have is like this, that 0 to t and 0 to 0 to, let us say, x and 0 to t and some function. It may be a function of x also, t and s and then ds and then this dt. This, you can see that this is actually equal to 0 to x and then s to x f. The change of order of integration will lead to this, that x t s, and now dt goes inside and ds comes outside. Okay. This is standard result in the change of order of integration, because you see what we are doing here, you have like this one inner variable. Initially you have s and then you have t here, and then this is the line t, diagonal line t equal to s. Okay. And then there is upper limit 0 to, this one is x and x here. So this is, you see that t variable goes from 0 to x and then s goes from this 0 to t. So, this is the kind of region where we are, this is the region where we are integrating this this triangle. Okay. So, when you change the order of integration, you go strips go like this. Okay. So, again this s will go from 0 to x, and then t will go from this to this. That means s to, because this line t equal to s to x. Okay. And the function remains the same there. Okay. So, now this one will then, using this, will get converted into, so if you remember what we have, so I will just simply use this one, I drop this. So, the change of order of integration will lead to this a plus bx plus 0 to x, and now s goes out, t comes in. There is nothing there with as a function of t. So, you what you will have is simply this s to x and then dt, and you have fs ds, right. So, this will give me simply x minus s. So, x minus s fs ds, and I can then change this s to t, because those are dummy variables like this, and same thing goes with that lambda 0 to x and then x minus t y t dt. Okay. So, here this f is a known function. So, overall this is some function g x and then minus lambda 0 to x and some function k x t y t dt. Okay. So, what you have is finally this equation. So, that is a Volterra equation, and here k x t is nothing but x minus t. Okay. X minus t here. This is everything is a function of x, which we write as g x here. Okay. So, that is a Volterra integral equation. Okay. So, an initial value problem, you may have now certain even nonlinear terms here. So, there may be a nonlinear kernel coming there inside whenever you have initial value problem there. Okay. Now, for a boundary value problem, so if you take this y double prime plus lambda y equal to f x, and now this equation is to be satisfied inside this 0 1, let us say, for simplicity, and then you have certain boundary conditions that y 0, again boundary conditions can be very complicated also, but we will take very simple condition, endpoint conditions, that y 0 is a and y 1 equal to b. Okay. Usually you have an SLP, then you know the general SLP is like that you have certain r there, r x y prime prime plus q x plus lambda r x y of x equal to 0, and then you have boundary conditions like k 1 y a this 0, or you may have a less than x less than b, and then y a plus k 2 y prime a equal to 0, and L 1 y b plus L 2 y prime b equal to 0. That is a general SLP. So, it is a particular case of that SLP there, right. Here these may also be non-zero kind of things there, and you may also have certain periodic conditions also, like here you may have that y 0 equal to y at 1, these kind are called periodic boundary conditions. So, those are not included here. You have those are separate periodic boundary value problem, but for simplicity we will deal with this. Now, how to convert this to an integral equation? We follow the same procedure and see what we get. So, again the first integration will lead to that same one, that y, of course we do not know y prime 0. So, y prime x equal to y prime 0 and plus integral 0 to x f t dt minus lambda 0 to x y t dt. Is that okay? And now again integrating it, so you get y at x. Now y 0 we know, so y 0 is a and plus y prime 0 x plus these things you get in the same way, 0 to x, x minus t f t dt and minus lambda 0 to x, x minus t y t dt. Okay. So, this is the unknown here, we have to find. Okay. And for that we will use this condition is already used, we now use this one, and so substitute y x equal to 1. So, y 1 is b. So, we get b equal to a plus y prime 0 plus 0 to 1 minus t f t dt minus lambda 0 to 1 minus t y t dt. Okay. And so, now y prime 0 is determined from here. So, that is y prime 0 is b minus b minus a minus 0 to 1 minus t f t dt and plus lambda 0 to 1 minus t y t dt. So, substituting that here, then we will get the corresponding integral equation. So, let us see that. So, what we have is now y x equal to a plus substituting. So, you multiply this by x. So, this is into x here and x here. Okay. So, a plus okay, b minus a into x plus sorry, this is minus here, minus 0 to x, x into 1 minus t f t dt plus lambda 0 to x, x into 1 minus t y t dt, and then the remaining terms there, plus 0 to x, x minus t f t dt and minus lambda 0 to x, x minus t y t. Okay. Now, so this looks like a very complicated one. We want to simplify it. We break these sorry, it was 0 to 1, 0 to 1. Okay. 0 to 1. Now, we break this integral to two parts, 0 to x and x to 1. Okay. And so, 0 to x will be added to this, and so what it leads to the following, that you have a plus b minus a into x, and then you have with f t we will. So, how we write that? I will write that like this 0 to 1 and some function k x t f t dt, and then plus similarly for the other one lambda 0 to 1 k x t y t y t dt. Now recall that from x to 1 it is simply this, and for 0 to x this I mean this minus that, okay, and it's a simple calculation actually that this k x t comes out, and same thing happens for that also with the minus sign. I mean plus becomes minus or minus become plus, like that. So this is actually the kernel, this is t into 1 minus x whenever this 0 less than t less than x less than equal to 1, and this is x into 1 minus t whenever 0 less than x less than equal to t less than equal to 1. Okay. So, and this part is simply your okay, the whole thing you can write it as gx, and this is the integral operator part. So, what we got now is a Fredholm integral equation. So, we get now this y of x, or now I will write it as phi of x equal to f x, or so all that gx I will now write as f x plus lambda 0 to 1 k x t y t dt. Okay. So, this is a Fredholm integral equation. All right. So, whether we have an initial value problem or we have a boundary value problem, correspondingly we have respectively either this Volterra integral equation or Fredholm integration. Now comes to the main point that how do we apply this fixed point theory. Okay. So, now so for that the unnecessary details we suppress and write it as an operator equation. So, what we need to solve is this phi equal to f plus lambda, and this we write it as operator k of phi. And what is that operator k? K phi at x is, in the Volterra case it is 0 to x, or we can write it like this also 0 to 1 k x t phi t dt, where in the Volterra case this kernel k x t is simply that, let me write it as k1, it is simply that k x t, okay, when I mean, and for 0 less than x less than equal to t, and it is 0 for this less than equal to 1, and 0 less than equal to t less than equal to x less than 1. So, the other part it is 0, and for so it is in the Volterra equation case it is like this, and for the Fredholm equation it is simply k1 x t is over that k x t, right? Is that clear? And here that k x t in that Volterra case maybe is different. So, let me okay, let me not get into the complicated thing. For Volterra we have like this, where this is k1, and for Fredholm it is actually over this k 0 to 1 k x t phi t dt. Okay. Now, so so we look at this operator equation and we define the operator t. Now we have to first specify where we are going to consider this. Okay. So the simplest one would be when we have this x as C 0 1. uniformly continuous functions, the space of that, and the norm, you know, that supremum norm is considered there. And so here we have these functions also continuous, and this function f is also in the, this is actually from k is from then 0 to 1 cross 0 to 1, and it may be in general a complex number. Okay. And so these are also, this space is complex valued continuous functions. So it's a complex Banach space. Okay. Now here, okay, so we define this T from this x to x like this, that T of phi equal to f plus lambda k phi for any phi in x. So now we look at t to the power n here. What happens to that? Does it converge or not? Huh? So that's where, if it or is it a contraction or not? And if it's a contraction, then we know from Banach contraction principle that it will converge to a fixed point, unique fixed point, phi 0. Okay. So let's look at the sequence Tn. So you have now, let's say, t square of phi. So t square of phi is f plus lambda k. T square of phi is t of t phi. Okay. So here you have to simply replace this t phi and substitute that t phi there. So you have f plus lambda k of f plus lambda k phi. You see, even though k is a linear operator, t is not a linear operator. Okay. So there is no restriction of linearity there. You can go to even non-linear kernels there. Under certain restrictions, we will have our result for that too. So continuing this way, what happens here? So this actually comes out, this f plus lambda kf plus lambda square k square phi. So by this it keeps on shifting. So t to the power n phi will then be f plus lambda kf plus lambda square k square f and so on, plus lambda to the power n minus 1 k to the power n minus 1 f plus lambda to the power n k phi. Now k is an integral operator. How do we see that? What are these k square, k and so on? Are they also integral operators or not? So it happens that they are also integral operators. So let's see that. So this is true whether you consider the Volterra equation or Fredholm equation. Okay. The only thing is, when you consider the convergence part, that's where now things will differ. And you see that what is t square. So if k is what is k square? So k is like this, k phi of x in the Fredholm. Now we will first consider Fredholm and then we will deal with the Volterra. So 0 to 1, this k x t phi t dt. Now k square of phi x, then it will be 0 to 1 k x t, and here k phi t dt, right. And so now just substitute that k phi t. So 0 to 1 k x t, and here then 0 to 1. Now we'll have to change the variables, that k t and let's say s, and then you have phi s ds and then dt. Okay. So now the change of order of integration will give us this 0 to 1, and then so this s goes out, so phi s will go out, and you have this 0 to 1 0 to 1 k x t and then k t s and then dt and then phi s ds. Okay. So, I just to keep things in a simple order, what we do, we just change the dummy variables. So, we will write this as s, interchange the t and s. Okay. So, s here and t here and ds here and then phi t dt. Okay. Does not matter, those are dummy variables, you can rename them in any manner you like. So, this k square, this is the kernel of k square. Okay. So, we write this as k 2. So, we will have this k 1 x t is simply k x t, whatever kernel we have there originally, and then k 2 is this. So, k 2 x t is 0 to 1 k x s and then k k x s and then k s t d s. Continuing this way, we will have now since k square is the integral operator. So, again you take k with k square, that is repeating the same process, it will also be an integral operator, and you then have these kernels. So, this k n plus 1 x t is the kernel for k n, this is the kernel for k n plus 1 operator, which is 0 to 1, and then you have you can write k n here, or I mean let me first write and then k x s and then k n s t d s. And by symmetry you will see that whether you write n here or here, it does not matter, it is the same thing, that 0 to 1 is k n x s and k s t d s is the same thing. Okay. So, it is not that you have to remember you write k n here or here, it does not really matter. Okay. So, those are all integral operators, and so continuing this way, what we get finally the following series, that is called Neumann series. So, here so what you have is then as I intend to infinity, what you will have if we by some way we ensure that this t is a contraction, then it will go to some phi 0, and that phi 0 is going to be a solution there, right, because if phi 0 is a fixed point, then you see that t phi equal to phi, and then phi equal to let us say phi 0 is a fixed point, then phi 0 equal to t phi 0, which is nothing but f plus lambda k phi 0. Okay. So, then phi 0 is the solution, right, and it is a unique solution for that, provided this t is a contraction. Okay. And we will see that under what condition this turns out to be so, or later on we will see that t to the power n is a contraction, and then by that generalized result we will have a fixed point of t, which again then gives a solution, and it will be a unique solution for that integral equation. Okay. So, let us see now what we are getting, that then this phi 0, in case it is ensured that we get such a phi 0, then you have that phi 0 is f plus lambda f lambda k f plus lambda square k square f and so on. Okay. So, this if you write it in an integral form, what you get is this phi 0 x equal to f x, and then you take out that one lambda, and then you write these are for Fredholm it is 0 to 1, and then the first one is that k1 xt, and then here one lambda is gone out, so plus lambda of k2 xt and so on, and then you have ft dt. Okay. So provided this series of kernels converges, then what you get is the following, that f of x plus lambda 0 to 1, this is called resolvent kernel. It is like this because it's a function of lambda also, lambda and xt and ft dt. The solution phi 0 is given by this. Okay. Now everything is known here. This provided this converges, you know that limit is that resolvent kernel, and f is known here, so phi 0 is known by that. So you need to just get that this sum of these no, this series you have to sum up in order to get the solution. Okay. Once we are ensured that this T is actually a contraction. So let's look at that when it is going to be a contraction, at least in the Fredholm case, and then we will see that in Volterra case it is much more simple. There are no restrictions on lambda as such. Here this we will see that for a small lambda this series will converge, and for that you see that here what you get is this series that f plus lambda kf, okay, plus lambda square k square f and so on. That so you know that it is something like if you ensure that mod lambda norm k is less than 1, then this series will converge. Okay, and it will actually be, it's the expansion of identity minus lambda k inverse of f. Okay. So this this will exist provided this condition is satisfied. Okay. So this and actually what you know is this norm of that little k0, because you know the kernel, and so you may have to get a slightly more restricted one, this one, that mod lambda to norm of little k0 little k of this is L2 of 0 1 cross 0 1. Okay, and this is simply the operator norm 0 L2 0 1, that, right, operator norm. So the condition is for a small lambda, you are ensured that this is indeed so. Now let me look at the Volterra case. So for Volterra case, we have these kernels like this. So again, so our operator, Volterra operator k phi at x is equal to 0 to x, that k x t phi t dt, and so k square phi at x will be then 0 to x k x t k phi t dt, and this 0 to x k x t, and then 0 to t you have k t s phi s ds and then dt. So change of order of integration, recall what I have explained there, you will get 0 to x, and you get that s to x, okay, and you have k x t and k ts going inside dt and then phi s ds. So, this is the again I change these dummy variables, we write it as t to x and s here and s here and t into just interchanging t and s. So, this is the kernel for k square, okay, and likewise you can get the higher order kernels. Okay, so then what we have is for the general one is that k n plus 1 x t equal to t to x k x s and then k s t d s and here or here it really doesn't matter. Now, we need to get certain estimates on this. So, what we have is the following estimate that k n x t will be let us say that k x t is a continuous function, the original kernel. Later on we will relax that and we will take the general L2 kernel. For the time being, let us take that k, because for that particular example what it was, simply k x t was that t into 1 minus x for t less than equal to x and x into 1 minus t for x less than equal to t. At least for that case this is a continuous function, right, and on this compact square it will be bounded. So, let us take that this k x t bounded by m. So, k x t is less than equal to m for all x, for all 0 less than x, t less than equal to 1. So, then what do we get? So, we will have actually so there is this estimate m to the power n x minus t to the power n minus 1 over factorial n minus 1. I think that is what I should get. Okay. So, let us see this. So, of course, for n equal to 1 you have that there for 2 n equal to 2 we have this one here k2 is like this, and what you get is okay, m square there and x minus t ds, right, and times norm of phi there. You actually have to okay. So, let me okay k2, let us look at k2 x t mod. So, that is actually equal to mod of y2 x k x y and then mod of this mod of k x t s and k s t and d s. So, m square comes out into x minus 1 simply. So, that is also okay for n equal to 2, n equal to 2, right, that matches. Okay. And so, by induction let us suppose that this is so, and then you apply that here. So, you have mod k n plus 1 x t is less than equal to then m to the power n plus 1, and you have t to x and s minus t to the power n minus 1 factorial n minus 1 here, and ds. Put this equal to u, and then at lower end it is 0, at upper end it is simply okay, x minus t and to the power n, and one more n here, and that matches with that. Okay. So, you have this estimate. All right. Now, we will look at this t to the power n. What happens to that t to the power n? Is it a contraction or not? Because that in the Fredholm case we had taken mod lambda less than 1, and you know that I have already shown that in the last lecture that for small lambda in the Fredholm case that is a contraction, and that is how we have got that phi 0 there. Okay. Now, in this case do we need any restriction on lambda? We will see that now. So, t to the power n phi is what? Recall that it is f plus lambda k f plus so on plus lambda to the power n minus 1 k n minus 1 f plus lambda power n k n phi. Okay. So, now looking at this difference phi 1 minus t n phi 2. So, that the first part cancels, that is common in both the things. So, you have lambda to the power n k n phi. This is a linear operator. So, you can write, or does not matter, you write it as k n phi 2. Okay. So, now we need to take the norm of that L2 norm. So, let us look at first this t n phi 1 x minus t n phi 2 x. So, that is less than equal to mod lambda to the power n, and then you have mod k n phi 1 x minus k n phi 2 x. Okay. So, squaring that square there, and then integrating it 0 to 1 and 0 to 1, then dx there, and substituting all that. So, it will be mod lambda to the power 2 n 0 to 1, and this k n has the kernel, that little k n. So, k n x t, and you have this phi 1 x minus phi 2 x mod of that dx, sorry, t dt, and then you have integral 0 to x there, right, and then finally dx. Now, so use the Cauchy-Schwarz there. Okay. So, you will get so mod lambda to the power 2 n, and then you have 0 to 1. Inside 1 you use Cauchy-Schwarz. So, you will have 0 to x mod k n x t square dt, okay, and square is also there. I forgot to put that is square there. So, that is square root will disappear, right, and then you have this norm phi 1 minus phi 2 square, okay, dt, and then dx there. Now, we had that estimate there. So, you putting that estimate here, and Okay, so you will have that m to the power 2n mod lambda to the power 2n, and that factorial n minus 1 square you will get, and then you have 0 to x, then x minus t to the power n minus 1 dt, and then norm phi 1 minus phi 2 square. Now this you can see that okay, yeah, oh sorry, e to the power 2n minus 2 like that. So this quantity is anyway less than 1, you can ignore that, and 0 to x dt. So this part is going to be bounded by 1, you can forget about that. And so now taking the square root, you will have this m to the power n. So our this norm tn phi 1 minus tn phi 2 is less than equal to, then taking square root, then you will have this lambda to the power n over n minus 1 factorial norm of phi 1 minus phi 2. Okay, is that clear? So now because of this factorial term here, choosing n sufficiently large, this quantity you can make less than 1, okay, without any restriction on this lambda. You choose a large n and you get this less than 1. Okay, so you so this is some k there which is strictly less than n. Okay, k n you can put some k n for that, you take a large n and fix that n so that this k n is less than 1, okay, whatever that k n is here. So it's a contraction, and therefore it will have a fixed point, and then you have this same Nyman series converging to that fixed point. Okay, so that actually gives us the solution. Now let me see some more, because yeah, I have some half an hour. So let's look at some examples. So if you consider this example, example 1, that phi of x minus phi of x equal to 1 plus lambda 0 to 1 xy phi y or xt phi t dt. Okay. So now our k1 xt is simply xt. Okay. So you, to get that, what is that phi 0 there, you need to just take that sequence kn and see whether it, for what lambda it sums up, and so you have, I think it's 0 to 1 only, no? Yeah, 0 to 1. So there will be a restriction on lambda naturally, because it's a Fredholm integral equation. So you calculate k2 xt, and what is that? K2 xt is 0 to 1, and k x x s and k s t d s, which is 0 to 1, and this is x s, and so x t comes out, and then you have s square and ds. So you get x t by 3. Okay, x t by 3. So this thing will keep on repeating. Let's look at one more, that k3 xt will be 0 to 1, kxt is that x, kxs is xs, and then now you have again this s square. So, xt by 3 will come out and ds, and then you get one more t there. So, xt over 3 square, and like that you will get that series in 3. So, what phi will then finally be, you can see that you have where does it x somewhere is cube by 3 only, no? Why it is getting 2 there? Is something I am missing or what? See, phi x, that fixed point actually comes out, or phi 0, it comes out to be 1 plus that lambda x over 2 summation lambda to the power lambda by 3 to the power n. Maybe I lambda n, yeah, to put that lambda also there, right? K2, K3, okay. So, x t by 3. K1, am I doing something wrong? Kx, yeah. This is okay as cube by 3, okay. So, I get xt by 3 and K2, maybe I am doing that wrong, K3, let us calculate K3. So, K3 xt equal to, you have 0 to 1 k xt and K2 x, K2 xs and k s t ds, and so it will be 0 to 1 k xs is what? This is xs and this is s t. So, x t s square ds only. So, I have x t s cube by 3, but one more 3 is there. So, 3 square, sorry, s cube by, maybe s cube by 3, 0 to 1, 3 square. Okay, so what I will keep on getting this, and I will get this, and then what you have is this series k1 xt plus lambda k2 xt, because one lambda I have taken out, plus lambda square k3 xt. This I have to see that what is this sum. So, there will one lambda will also come there, okay, and so you will have finally. So, okay, one lambda, and I do not know how one gets this 2, maybe there is something misprint, and so lambda by 3 you will have that coming to the power that, okay. Just check with how, I am not sure about the 2 there. So, what you have is this one. So, this will let us see that 2 is there, or I have some doubt. So, here what this will sum up to 1 plus lambda x over if 2 is there 1 minus lambda by 3. This will sum up to that. And you see that what you have here, this is provided lambda by 3 is or lambda is less than 3. Okay. This series will converge only for that. And so what this method only captures us this solution, and you see that for lambda equal to 3 you will see that there is no solution exists. Okay. For non-zero, because f is non-zero, so you will see that only homogeneous equation may have some solution there. For non-homogeneous one, for lambda equal to 3, there no solution will exist. Okay. And for lambda greater than for it's a complex mod lambda greater than 3, this method does not capture that solution, but you can see that for lambda greater than 3 this is valid form, right, and you put it in the equation, you will see that it satisfies the equation. So for lambda not equal to 3 you have a solution, but only this series method captures only the half part, okay, mod lambda less than 3. So that is a limitation of this method, but at least for a small lambda you have a unique solution there. Now
how do you say that lambda equal to 3 could be a solution here?
no, it doesn't. For lambda equal to 3 there is no solution. Yeah, because you will see for put lambda equal to 3 and then see that it does not satisfy the equation. Okay.
This one does not work.
This won't because it captures. You can show that you get a something absurd thing for which substitute lambda equal to 3, and for see because it's a non-homogeneous equation, you know that see when you have in the linear algebra also identity minus lambda this see or here lambda I, this lambda is coming in integral equation all.
Not clear from this. You have to do something.
You have to do something. You substitute lambda equal to 3 and look at this and put it in, plug it in the equation. You get something left side something else and right hand side something else. Okay. So that you have to separately look at. So lambda equal to 3 no solution exists because of the non-homogeneity here, non-homogeneous term here. If this is 0, then of course you may have a solution and then there will be infinitely many solutions. Okay. Like in linear algebra you have lambda I minus a, if this matrix A determinant is 0, then that lambda is an eigenvalue. Okay. And then you see that this lambda x minus a x equal to 0, for that one we will have a non-zero solution. So it's something similar to that. If this one is not there, let's say 0, then for lambda equal to 3 you will have a solution and there will be infinitely many solutions. Since it's a non-homogeneous, there will not be a solution. And you see that when do we have non-homogeneous ones, there is you see that the Fredholm alternative you have to use there, the orthogonality condition.
So I'll solution, the conditions which you have obtained, they are the sufficient condition, not necessary.
Not necessary, yeah, exactly, yeah. Okay, so that part, just I have some doubt about that one too, how it comes. So that's one, and so here that L2, this theory is only valid in L2. We proved the unique solution in L2. Outside L2, you can't ensure that, and there is one example like that. So if you consider this phi x minus 0 to x, y to the power x minus y, phi y dy equal to 0. Okay. So here, okay, yeah. So it's a Volterra equation, homogeneous Volterra equation, and here you can check that phi x equal to x to the power x minus 1 is a solution of this. Just put it in the equation, you can see that it satisfies that equation, because let's look at that. So here, so phi x is this, you have to check that this also gives you phi x. So that is 0 to x, and then y to the power y minus 1, and then you have sorry, y to the power x minus y, and phi y is y to the power y minus 1 and y. So what you get is this comes out, and y to the power x minus 1, okay, will come out, and so you will have yeah, one integrate that and substitute it, so it gives you the same function. So you have a, this is a solution. So and phi equal to identically 0 is also solution, right? So therefore what's wrong with this? There are two solutions. So uniqueness is actually kind of in the some sense it is breaking there. So is something wrong with our theory? No. What's wrong here is actually one can show that this is not an L2 function, okay. So we'll just show that this is not an L2 function, otherwise it will contradict our whatever we just established. So let's look at this one. So here if it is an L2, so what's this norm? It's 0 to 1 mod phi x square dx, and so this is anyway non-negative, so put it there. So mod, you don't need to put 2x minus 2 dx. This is because this is larger, the x is less than 1, so 2x will be less than 2, and so it's in the denominator, so it's actually improper integral. So this is limit epsilon tends to 0, epsilon to 1, x to the power 2x minus 2 dx, okay. I will show that this actually becomes infinity, and therefore this is not an L2 function. So let's see that. So let's put x equal to 1 over y, okay. So then it is limit epsilon tending to 0, 1 over y means this will become 1 over epsilon, and 1 remains 1, and 1 over y to the power 2 over y minus 2, and here you will get a minus sign because of that 1 over y square minus y square. So the dy over y square, okay. So this minus 2, this you can remove then this y square with this one, so you get that, okay. And so 1 over epsilon tending to 0 means 1 over epsilon tending to infinity. So you can rewrite it like this, that putting 1 over epsilon equal to r, so that is then adjusting this minus sign, so limit r tending to infinity, and you have 1 to r and 1 over y to the power 2 over y and dy, okay. And that will be greater than equal to limit r tending to infinity 4 to r of 1 over y to the power 2 over y dy, okay. So for y greater than 4, this 2 over y will be less than 1, okay. 1 over y is less than 1, so a smaller power will be larger, and so this is greater than equal to limit r tending to infinity 4 to r over dy over y. So that is limit r tending to infinity ln of r minus ln of 4, and so that goes to infinity, okay. So it is not an L2 function, so we are kind of safe there.
No. I think more fundamental reason for not getting it applied to those functions lies in the consideration of Hilbert spaces.
Yeah, Hilbert space, exactly, yeah, yeah.
Which L2 is there, but
yeah,
other non-L2s are not there.
yeah. So is it? Should I stop or? Huh? Okay. So maybe I'll do one more result. Let's just.
It's up to 11.
Yeah. Okay. Okay. I'll do that.
15 minutes maybe.
Yeah. Now, as I wanted to do that for extending it to L2 kernels, because here we used the boundedness continuity. So, we want to get rid of that continuity thing. So, now we will assume that this little L, this k little k is in L2 0 1 cross 0 1. Okay, then so again we want to show that for some large power of t it will be a contraction. So here we need certain notations. So our equation is that phi of x minus or equal to fx plus lambda 0 to x kx t phi t and this k is in L2. So we now define these a square x as 0 to x mod kx y square dy and b square y as y to 1 k x y square dx. Okay. And then you see that second integral of this will be because of this condition will be bounded. So those integral 0 to 1 of a square x will simply give you 0 to 1 here. So that is bounded by norm little k square. Okay, I am not writing L2 and all that, it's understood. Similarly, this 0 to 1 b square y dy is also bounded by norm little k, this little k, okay, square. So these are some number, let's say m, you can write a squares of that m, you don't need to write k square everywhere. And then we have another notation that rho of x equal to 0 to x rather than 0 to 1, that a square y dy. And then you have by that rho of 1 is less than equal to m, the same m there. Okay. So with this we look at t to the power n again. So our t to the power n of phi is f plus lambda a f plus so on plus lambda to the power n minus 1 for n f plus lambda k minus 1 lambda n k n phi. Okay. So that is our t. Now we look at these as before, we look at the estimates of the kernels. So here we will have this. So what is k2 then? K2 xy is y to x kx z k zy dz. Okay. So mod of this or square, yeah, so you take a square, and so this will be mod of the mod of this square less than equal to, okay. And then applying the Cauchy-Schwarz, you have this y to x mod kx z square dz, and then mod y to x k z y square dz, right. And then you can, in some you can go like y to 1, and in this you can go 0 to x. So you will have this thing will be less than equal to a square x b square y. Okay, like in the first one, if you put this one 0 to is less than equal to 0 to x, that will be a square x, right? And here this one x you replace by 1, and so that will be b square. So first on K2 we have this. Now on general K we want to show the following estimate. General Kn. So let's look at K3 and then go to the general one. So K3 xy will then be so this square will be less than equal to y2 x mod k xz square dz, and then y to x mod k2 z y dz square. Okay, and then you have, I think, yeah, that's okay, the square root will disappear. Okay, so now again you have to see that. So for K2 we use that a square x will be replaced by z and b square y, and here you will have, then again you have a square x b square y, and then y to x a square z dz. This you write it as 0 to x minus 0 to y. So this you can write it as rho of x minus rho of y. So we get the pattern now, which we will show by induction. So general Kn, or yeah, general Kn, we want to show this is a square x b square y and rho of x minus rho of y to the power n minus 2 over n minus 2 factorial for n greater than equal to 2. Okay, first few I have already shown, and assume this, and then go to Kn plus 1. Okay, so when you take Kn plus 1, so you have Kn plus 1 xy square is less than equal to y to x kxz square dx, and then and then okay, so square root applying after that Cauchy swap dz, and then you have y to x mod k z y square d k n dz. Okay, so putting that here, and here what you will have is that a square z there. So a square z, and this you have this term there. So rho of z minus rho of y. This you will take out. So rho of x minus rho of y, you will put some u, let's say, and then that you get rho of z prime. But rho of z prime is nothing but a square z. So it's you will get then finally the 1 power raised upon that. So that proves the this estimate. Okay. Now you look at Tn and show that it's a contraction for some n, and we are done. So now look at this Tn of phi 1 minus Tn of phi 2, and this at x square. So it will be less than equal to mod of this 0 to x k n of x y, and then phi 1 y minus phi 2 y. Phi 1 y minus phi 2 y dy square. Okay, and again applying the Cauchy-Schwarz, or we don't need to, I think, yeah, Cauchy-Schwarz you apply. So you have 0 to x k n, then will be bounded by this a square x b square y over n minus 2 factorial, and then rho x minus rho y to the power n minus 2, and okay, and dy, and then you have this term norm phi 1 minus phi 2 square. Okay. So here okay, a square, so here you can take rho of rho y, you can drop, and you can take rho 1, and you have factorial, this thing will come out, and you have this a square x and rho of 1, rho of x, y you drop, so rho of x to the power n minus 2 over n minus 2 factorial, and this integral of, sorry, this integral 0 to x b square y dy, this you can write 0 to 1 then finally, 0 to 1, and then you have phi 1 minus phi 2 square. Now you integrate it once more with respect to x, and now you can take this rho 1 over factorial n minus 1, you can do it here itself in rho 1. So you will have this a square x dx, that is bounded by that m there, and so some bounded quantity m here, or m1 here upon factorial n minus 2, and this is also, so you will have that one more m there, let's say. So you have m square there, and m square over factorial n minus 2, I think it's square, is, it doesn't matter whether it's square or not. So it's a large quantity anyway. So you have this control over this term, okay, overall, something like some m1 over this n minus 2 factorial there. I think it should be square of that, because we had taken square, it should be n minus 1, some mistakes here in calculation, n minus 2 square, because we have taken that square of that, right. So after that, taking a square root, you will be left with this, okay, some m square is m1 or m1 square, you can write m1. So after taking that integral over that, you get some m square over factorial n minus 2 square, take the square root. So you have finally that norm of Tn phi 1 minus Tn phi 2 is less than equal to m over n minus 2 factorial there, and norm phi 1 minus phi 2. So it's a contraction for large n, and we have a unique fixed point. So I will stop here. Okay.
you very much, sir, for your nice lecture. Of course, I miss this part.
But you know
because
all
I'm
those
busy
things.
in other issues. So if you have